All right, direct variation. So, we're going to go through a couple examples of things that would be direct variations. Okay? And a direct variation has some distinct features. First of all, it must go through the origin of a graph. Okay? Now, I've only drawn one quadrant of a graph, and a quadrant is a fourth, right? We're used to seeing graphs that kind of do this, right? Where we have positive x values, positive y values, negative x values, and negative y values. Direct variation represents a graph that goes through the origin. The origin is when y and x are both 0. Okay? So all direct variation must go through 0 and 0. Otherwise, it's not direct variation. And we'll get into equations that look like this. But what we want to talk about is Dave gets paid $10 an hour. Okay? We want to represent this. So on average, okay, if we're talking about hours, most likely what's happening is he's working an hour at a time. So we'll go up in increments of 1, 2, 3, 6, 7, right? And then our y values, maybe we'll go up in increments of 20 here. Yep. And what we're going to be doing is we're going to graph all of Dave's potential earnings. And in fact, let's say that Dave is only really able to work 8 hours a day. That's usually a shift. Okay? So if he's only able to work 8 hours a day, Malik and Charm, what would he be getting if he works 0 hours? How much money would he make?
0.
He's making no money, okay? So, and actually we should have talked about this. What are the two variables in here?
Hour and pay.
Hour and pay, that's right. So hours worked and his pay. And let's talk about, and I already wrote them all over here, but which would be the independent and which would be the dependent variable? Hours is what? Independent. Which means what axis does it go on? X, that's right. And pay would be the dependent, which means it goes on the Y. Now, we talked about this, I think, the other day, hours. Anything we're dealing with time, almost 100% of the time goes on our x-axis. Okay? There's not many things where time depends on them. Okay? Maybe if you're building a clock. Otherwise, it's usually our independent variable. So, with this being said, our very first point, when he works 0 hours, he gets how much pay? 0. Right? He gets no money. If he doesn't show up to work, they don't pay him. What if he works 1 hour? 10. Okay, good. What if he works 2 hours? 20. 3 hours? Good. And 80. Excellent. Okay, so we know by looking at this that this is a linear relationship, correct? This is a straight line. It has a linear relationship to it. And it's constant. It's constantly changing by the same amount. We go over an hour, we go up $10. Over an hour, up $10. Okay? So this is going to be important later on. So every time we went over by an hour, his pay went up by $10. Okay? And this essentially represents all the potential earnings Dave can make. If he works 0 hours, he gets $0. If he decides to work 4 hours, we know that he's going to get this point here, or this coordinate, of $40. And as a coordinate, we always write our x and then our y. This coordinate here would be 4 and 40. So this is a graph of Dave's potential earnings. Okay? It's a direct variation because it goes through our 0. So let's talk about a few other direct variations. All right, since we can't really think of any, I'm going to come up with one. Let's say we're driving in a car, okay? And I put on cruise control. So we'll say that Mike is driving. He just got on the highway, and he's speeding. He's going 110 kilometers per hour.
What? He deserves it. My mom drives at 120.
Okay, so first of all, what is the independent and what is the dependent variable? What's our independent? His hours, his number of hours that he travels, right? That'll be independent, in other words, our x-axis. What would be our dependent variable? Kilometers? Yeah, okay. to our kilometers. Our kilometers depend on the amount of hours we've been driving for. So that goes on our y-axis, okay? So let's try to imagine somebody driving in a trip. Again, we're going by hours. So we're going to start at 0. And this time, again, we'll go up by... Actually, let's go up a little more. Let's go up by 2. So we'll change this a little, okay? Just so we can see the difference. Thank you. Okay. And then these ones will go up by 200. And there's going to be a reason we're going up by this much. The reason I've done that is I want you guys to think about this quickly. If you were to go 2, that means he's going how far after 2 hours? 220, okay? If I was going up by hundreds, that would be way up here. By the time we get to 4, we'd be way up here. I'd be off this graph very quickly. I want to be able to represent it with a much less steep slope. So I decided to increase my y value, the increments. As we change increments on a graph, we can manipulate what the line looks like. Okay? So what's very important about direct variation? What must it go through?
200, 400, 600.
What must it go through?
100.
No.
Sir, I think the y-axis should...
Okay, it must go through the origin. So, in other words, if we travel for no hours, do we go anywhere? No, we don't. So the origin is obviously part of this. So this is a direct variation. Let's go up by our hours here. Now, this is what's tough. We need to use an equation to represent this. Okay? And usually when we have equations, we have a y and an x. Okay? And we usually set up y is equal to, and we're going to use another variable. We're going to call it m. This m is our slope. Okay? This is how much our y is changing by. And in our very first example, if I was to make an equation out of it, we'd have y is equal to, and again, we've got to figure out m, x. So this represents how much is our y changing relative to x. So every time we went over 1 on x, how much would our y change?
1 up and a half.
How much did we go up? Not a half. What was our value? 10. We were going up by 10 every single time. So our m in this case is equal to 10, which means our equation is y equals 10x. Okay? So with that being said, before we go through this, what do we think our y is changing by relative to x, Charm? Our m is what? What is it? That's right. Our m is 110. So for every 1 that we change on the x, for every hour we travel, our y changes, or our kilometers change by 110. So our equation is represented, or it looks like y is equal to 110 x. Okay? And we can use that to calculate all our points on our graph. Okay? So for instance, we know by looking at it very quickly, if we go 1 hour, how far do we go? 110. If we go 2 hours, how far do we go? Yeah, 220. That's pretty easy to calculate. Well, not very linear, though. What if I quickly asked you if we were going 12? How far do we go? It becomes a little difficult. Okay? If we were to go for 12 hours, how many kilometers? And the best way to do this is 12 represents an x value. So I can plug in 12 for x, and it will tell us our y value. So we use the equation from here. We have y is equal to 110. And if we're trying to figure out 12, okay, remember this was our x. Yeah, we're going to times it. So we're going to replace x with 12. So we replace x with 12.
I calculated 1320.
Is that what it is?
Yes.
Good. That means our y would be 1,320. So this equation will help us when it comes to our graphing. Now, obviously, on this graph, that kind of puts us way off the chart. 12 is a little far for us. But we can use that information to find specific points in our direct variation. So let's continue this graph. We know it needs to be linear also to be direct variation. What would 400 give us? 440, which is maybe there. 600? 660,
880.
880, probably about there. Okay? And we know that this is a linear relationship minus the one I kind of... Yes, yes.